Hello students, in this lecture we will discuss about the totally disconnected space, and it is also known as a maximally disconnected. So first we have a definition of totally disconnected space. A space is totally disconnected if for each xy belongs to x, and these are distinct points of x, then there exist two open sets u and v such that one is containing x point and other is containing y point, and x is a union of these open sets. So x is a union of u and v here, so it is a disconnection of x here. So we can say that totally disconnected set can be separated by a disconnection of x. So now for example, in the first example we have set of real numbers with the upper limit topology generated by half open intervals, which is open with a and closed with b, is totally disconnected. So in the first example, if we take set of real numbers with the upper limit topology, which is denoted by tau ul, it contains all half open intervals here. So these are open in this topological space, and we have to prove that it is a totally disconnected space. So if we take two elements from this space which are distinct with x less than y, then there exist two disjoint open sets in R, that is minus infinity to x, which is open with minus infinity and closed with x, and x to infinity, such that x belongs to minus infinity to x interval and y belongs to x to infinity because y is greater than x here. And also if we take union of these two open sets, then we will get real line here. So it is a set of real numbers. So from the definition of totally disconnected space, we can say that set of real numbers with the upper limit topology is a totally disconnected. So now in the second example, set of real numbers with the usual topology is not totally disconnected, and we know that usual topology contains all open intervals. So these are the open in this topological space, and there does not exist any pair of two open sets which are disjoint and satisfy the totally disconnected space definition. So in the second, R with the usual topology is not totally disconnected. Actually this space, that set of real numbers with the usual topological space, is a connected space. So now we discuss some results based on the totally disconnected space. So our first result is every discrete topological space is totally disconnected. So for the proof, let X be a discrete topological space. Then we will prove that it is a totally disconnected space. So for this, let us take two arbitrary elements from X, and these are distinct elements. Now we define U here, which is singleton X, and V, which is X minus singleton X. And X is a discrete space here, so as X is discrete space, and we know that any subset of X in this discrete topological space open as well as closed. So these U and V are open in X, and also here we can say that it is a singleton X, so X belongs to U, and if we take any Y which is distinct from X also belongs to V with, if we take U union V, it is X only, because if we take X minus X, singleton X union with singleton X, it is X only. So which proves that X is a totally disconnected space. So in this result we will prove that set of rational numbers, that is a subspace of set of real number, is totally disconnected. So for the proof, let us take R1 and R2 two rational numbers. These are distinct rational numbers with R1 less than R2. So here we have a one result in the calculus, that there is a irrational numbers between two rational numbers. So there exists an irrational number we take t here, such that R1 less than t less than R2. Now if we take minus infinity to t open interval here and another open interval t to infinity, so these are open in set of real numbers, and q, which is a set of rational number, is a subspace of set of real numbers. So as q is a subspace of R, then if we take intersection of q with this, with these open sets, that is minus infinity to t intersection with q and t infinity intersection with q are open in q. And here we have a two rational numbers R1 and R2 with R1 less than R2. So from these open sets we can say that R1 belongs to this open set and R2 belongs to another open set here. And also if we take intersection of these two open sets, it is empty, because these two open intervals are disjoint, so this will be empty intersection. And if we take union of these two open sets, that is minus infinity to t intersection with q union with t to infinity intersection with q, then it is q only. So which implies q is totally disconnected. So in this result we will prove that the components of totally disconnected space are singletons. So it means in the totally disconnected space only singletons are the connected subspace. So for the proof, let X be a totally disconnected space then we will prove that the components of X are singleton. So for this we have to show that no 2 points subspace of X is connected. So for this let us take C, which is not singleton, subspace of X. Now if it is not singleton, then we can take any two arbitrary point of X, which are point of C, and these are distinct also, and it is given that X is a totally disconnected space. Then from the definition of totally disconnected space, there exist two disjoint open sets, that is U and V in X, such that U is containing X element, V is containing Y element, and X is equal to U union V. And here we have taken C is a subspace of X. C is a subspace of X. Then if we take intersection of C with these two open sets of X, then we will get open sets in C here. Then U intersection with C and V intersection with C. So these are open in subspace C. Now if we take union of these two open sets, then U intersection with C union V intersection with C, so it is equal to U union V intersection with C, and U union V is X here, so X intersection with C, as C is a subspace of X, so it is C. And also if we take intersection of these two open sets, it is U intersection V intersection with C, and these are disjoint open sets in X, so it is empty, intersection with C, so it is empty. So which implies that C is disconnected. So here we have taken C, which is not a singleton subspace of X. So if we are taking any subspace other than singleton, that is a disconnected space, intersection with C, so it is empty. So which implies that C is disconnected. So here we have taken C, which is not a singleton subspace of X. So if we are taking any subspace other than singleton, that is a disconnected space. And we know that singletons are connected in any topological space. So from here we can say that only singletons are the connected subspace of a totally disconnected space. So in other words, we can say that a totally disconnected space has no connected subsets other than singletons. Now from the definition of totally disconnected space, again we conclude one result here. So this is simply from the definition of totally disconnected space, that is every totally disconnected space is T2 space. Or we can say that every totally disconnected space is host of space. So if we take X here, which is totally disconnected space, and we take two elements from this space which are distinct, so then from the definition of totally disconnected space, there exist two disjoint open sets U and V, such that X belongs to U and Y belongs to V, such that X is equal to U union V here. So from here we can say that if we are taking any two arbitrary points which are distinct points, then there exist two open sets here, disjoint open sets. One is containing X point and other is containing Y point. So we can say that it is a T2 space also. So from the definition of T2 space, we can say that X is T2 here. and here T2 is a separated by two disjoint open sets, and here totally disconnected space is separated by disconnection of X here. So this is the difference between T2 space and totally disconnected space, because this is not true in the T2 space. So in the next lecture we will discuss about the path connected space and its component. So thank you.